Hey, hey everyone. Um, just like some reminder things. Are everybody of you in the group link, right? Raise your hand if you're not. Everybody's. Okay, so just like I published the recording of first lecture there, and it's gonna be like a YouTube playlist with all the lecture recordings. So if you missed something, or there's I don't know, you get distracted for a little bit, you want to rewatch something, you can go there. I'll update it weekly. I also send the book to the rookie, so we can access it for free. Yeah, and there is also a Google form with for feedback if you want to add any ideas, but I'm also happy to talk to you in person.
Yeah, we'd be glad to like go over it in class and like discuss the results, sort of like trying to improve the lectures and also maybe plan events that everyone would be interested in. Like maybe some people don't like movies, that's totally okay. Instead, we could do board game night or some other social events if you guys would be interested, stuff like that.
Yeah, somebody said skiing in the forum.
We would also be down for skiing if we can.
Okay, yeah, so let's get to our handouts, and so. So I'll start with just like leftovers of chapter 2 that we started last time. And then Bonnie will pick up on the multiple Cuban system. Just make sure.
Don't worry about that just yet.
Yeah, just yet. Don't worry about that. Just make sure. Are you in the group me? Okay. Okay. Anyway, so in chapter 2, you can see the terms like global space and relative space. And generally speaking, global space doesn't have any physical meaning, and it's not really used anywhere further. So we're not gonna talk about it much, just because it is that it's not really used. But there is another thing called global space. Global. Sorry, relative. So. And so the problem with quantum states is that we already defined that, okay, the sum of amplitudes squared should be 1, and that's what we know for sure. But the problem with quantum states that we're defining is that if we just have same amplitudes, it doesn't really mean that states are the same. And we should actually look in more details into the geometrical interpretations of each qubit, which we will go over in a minute. But basically speaking, we'll define relative phase as the modulus of complex number. This one. That satisfies the relationship, which is also written down in the notes. Is this.
Physics.
And so for those of you who are less familiar with complex numbers, we just say that I squared is -1, and there is also some Euler formulas that we can use if you know the number that is x plus iy. We can actually express it in the form of just thinking about it. Okay, so we can say that, for example, let's say C is some kind of R, which defines the whole magnitude of our vector, and we say that it's sine theta plus I sine theta, and this whole thing is defined as this. So then we have the B is R EI later, and for our case, we know that the sum of amplitudes is amplitude squared is equal to 1, so R should also be equal to 1. We're talking about the magnitude of output. So that's like some basic stuff about complex numbers. Don't worry about it, you don't get it all together if you're new to that. We won't really use it that much. It's just for you to break down some concepts in quick. And the other concept that actually will be a little bit more useful is called Bloch sphere. So we went over it last semester a little bit, but just to remind you, that's a geometrical representation of our quantum state. And this is a 3D sphere. And basically, it shows us the reasoning behind introducing quantum numbers, complex numbers, to our quantum state. Is that because if we only had, let's say, 0 and 1, it would be harder for us to describe way more states. And when I talked about different states having like same amplitudes, A and B, when I'm talking about A and B, talking about this thing. So the problem with that is that if we draw two vectors in sphere, and let's say A squared have the same like magnitude here and here, and then B have the same magnitude, but we know that these are different states, and that's why we introduce basically complex numbers. And we define some other points on this Bloch sphere, which are basically pointed out on your handout too. So what is plus and minus? We talked about plus sign a little bit, but basically plus and minus are defined as Hadamard bases. So we know that just for the sake of convenience, last time we chose bases as 0 and 1, but there and when we talk about polarization, 0 and 1 can be described in this way, which is basically a so-called polarizing filter with polarizing axis directed either in this direction or this direction. So all the photons going through this filter will be polarized in upward direction, or these ones will be in left direction. But Hadamard basis is when photons polarized in this direction and this direction. And basically it doesn't really matter which basis we use, and that's like one of the concepts that we use for quantum encryption and so plus is basically the state of 1 square root of 1, 0 plus 1. And then minus is 1 0, which corresponds to these two vectors. And so we just basically define these 2 points in here. So if we draw a vector here and here, that would be this plus and minus vectors. But there's also state.
Are there any questions so far?
Yeah. Feel free to just like stop me and questions. There's also state I and minus I. And again, introducing complex numbers here just gives us a little bit more space and defining different quantum states. As we said, they can have the same amplitudes, but because we're now extending with like minus I and I dimension, we can talk about way more quantum states than before. And I think Danny will might go over Bloch sphere a little bit more.
Yeah.
But yeah, Bloch sphere is not physical qubit. It's more like a mathematical interpretation of how we can actually visualize everything and how like quantum states evolve. So it's not like how if we look at the hardware, that's how it looks. It's just like mathematical tool, I would say. Okay.
And the relative phase is sort of like I guess in relation to like, say, the plus or minus axis is just the projection of that vector that you can draw on the sphere.
You can also draw it,
Right.
but I'm done with my wording.
Oh, yeah, sure. In I'll go over it more, in the future, it'll be like a useful visualization tool once you get like Qiskit and stuff, which is really simple, it's just, like high schoolers can learn it, it's like this, Python package that you can use for quantum simulation and stuff. And for building your own circuits, testing out your own ideas. And on the block sphere, you can just think of the,
Oh, wait. Marker. No, the green one is not visible.
okay. Say it's like a vector on the sphere. That sphere. Uh. So the B would be a phase for this, these, while the A would correspond to a projection onto this plane. And we might go over it more later, when we actually get to using it, but for now, are there any questions before we move on to like multi-qubit systems, which is really where like the actual, I guess, quantum computing properties start to arise as we treat like qubits interacting and stuff. I mean, we won't like go over that in depth today, but I might like mention like some, I guess, circuits as well as some phenomena in multi-qubit systems. Okay, so the general form of the general form of a single qubit, which composes an n-qubit system, is this. So each component has a relative phase. And of course, you can also generalize it to give it a global phase, which, well, in most cases is useless. There are certain algorithms like Grover's search algorithm, which does use it. So it's useful sometimes. And when you measure this state, say like, if you look at the diagram in figure 1 on this one, in a circuit, these I guess probe or meter symbols are indicating a measurement. They'll collapse either to a 0 or a 1. And that's when a qubit becomes a classical bit. So the quantum aspect of a qubit only exists before we measure it. So the gates also depicted on that diagram are sort of how we manipulate it. And you can see them kind of right there. But before that, we have to understand how these multi-qubit systems are represented like mathematically, so that we then can manipulate them with those matrices. And I guess we get to like understanding the, I guess, oh, sorry. I guess it's not a portion. Does anyone mind if I erase this or? Okay. So. Say we have two qubits, psi one. And psi two. And, or maybe five. And they're in a circuit. So we want to understand how their states interact and how we can represent them using one, I guess, mathematical construct. And to do that, we have to take a tensor product. So a tensor product in this ket notation, and I guess you don't know what this is called a ket, which is really just a matrix or a vector, sorry. That forms a linear vector space. So if you measure for a 0 state and a 1 state, which is equivalent to sort of this operation, you'll get 0. And times this by this, add them together, get a 0. So in that sense, that's how you should understand these kets. They're completely different orthogonal or perpendicular states
Hey, Dan,
that.
can you just briefly mention for those who are new to bracket notation, what is bra, what is ket, and how they organize?
Sure, so kets are these and bras are these, which is basically just reversing the ket. And a bra ket is when you take the product of them. Sorry, can you guys see? You take the product of them and you get a probability amplitude. And measuring two orthogonal states will give you 0, and anything else will give you phase. Like say, if you were to measure 1 to 1 for 0 to 0, you would get A and B respectively in that equation. So understanding how these translate to matrix form, taking the tensor product is equivalent to effectively doubling the
You can also pull up tensor product formula and apply it. For those who don't know. But it's, yeah, that's just like, for those who don't know, it's just like, there's an algorithm, but it's nothing crazy. You just follow the steps.
Yeah, in terms of matrix form, I might have gone a little bit. I think you have to, what?
I think a tensor product of two vectors is just a vector, it'd be like 4 tall.
Yeah,
No, I think that's a direct sum. Right?
but the result is a vector, not a scalar.
True. But in terms of bracket notation, the equivalent, as shown in, I think, equation 3 is you take the two kets and you combine their states such that you get all possible states for each quantum object together. So you get the 0, 0, the 0, 1, the 1, 0, and the 1, 1. And that scales exponentially. So depending on the number of qubits you have, you can have a potential for, say, 2 to the 5 classical bits, which I'm not super good at mental math, but 5 qubits turning into, say, I think it's 32, right? 32 classical bits is pretty impressive. And if you extrapolate that up to the hundreds, then you get enough classical bits where you need more, I think, it's an interesting statement where you need more silicon chips than there are grains of sand in the universe. So to like represent 100 qubits classically. Because of how the tensor product scales the information space that we're working with, or the vector space that we're working with. Now, the problem with that is that, yeah, it is a lot of information, and you can manipulate that information to get things that you want, but how you do that isn't exactly clear, which is one of the main problems with how these gates need to find a way to manipulate the phase in an algorithm to give you the quantum state that you want. And then in equation 4, I just show how classical bits scale. And although they're equal, technically in terms of the number of states, you'll notice that there's also not the phase component in the classical states, and they're just, the direct sum is basically just adding each classical state together separately. They don't like multiply together to create these compound states.
Can I add?
Go ahead.
The point was like number of say little sentences. So the reason why we need like so many numbers to describe the standard is basically in equation 3. You have two states, right? You have P1 and P2. And you have to describe all the coefficients before, like on the right hand side, basically. So when Donnie was talking about tensor, for those of you who like have hard time maybe mentioning it, it's like you have to define all the coefficients on the right side, like A and B. And that's why for classical system, you have to only define two numbers, 0 and 1. But for classical one, you see how many coefficients you have to define just for two states, because you have to define the probabilities to define this state. So that's basically where it comes from. And so it grows, I think, to the in an order of 2 to n,
Yeah.
to the power of n. So yeah, so basically you can say that for 3 qubits, you'll have 2 to the power of 3 number of coefficients you have to define. So basically it grows like that. Sorry, go on.
That works. And that scaling, I guess is one of the properties that is exploited. Another property, I guess in section 3.3 is entanglement, which you can see there are some examples of entanglement or entangled states, which is the phenomenon where you can't decompose an entangled state into the tensor product of two quantum states. So say psi and phi are in the basis of I guess 0 and 1 and all that stuff. Like the other way around. And that's set notation. You don't have to worry about that, but the point is, say you have a tensor product of these two states. That can't equal any of the Bell states described within equations 5 through 8. And what this means physically is that these aren't individual states. These once separate quantum states become one quantum state that you can't treat separately. So this allows for measuring one, I guess, component of the entanglement and knowing the other component simultaneously. So it's sort of like this idea of superliminal coding, liminal communication, which isn't physically possible, but in terms of like measuring one bit and determining the bit value of, say, like a photon that has been sent like that way, like a million light years away. And if they were still entangled for all of that time, and you measured the photon that was here prepared in the entangled state, you would know the state of that photon really, really far away. And that has implementations in communication, has implementations in error correction. Basically reducing the amount of I guess noise that the environment introduces, and also in quantum teleportation, which is depicted in figure 1, actually. That is a circuit used for quantum teleportation. And it might sound complicated, but really it's just teleporting one state onto another state. So it's like sort of the no cloning theorem being violated, quote unquote. And for those of you that missed the last lecture, that's basically just, you can't explicitly clone states. They're all unique. But using certain algorithms, you can copy a state with its phase totally up to another state. And well, we're not going into that. Because it's a little bit complicated. We have to know like the matrix representations and how these work with that. So
Get eventually there.
yeah. Are there any questions so far before I start to, I guess, wrap it up with my math? So yeah, the representing these multi-qubit systems and the formalism kind of shows how certain properties arise. And the more qubits you have, the more complicated it gets, of course, but also the more potential for information to be extracted, more phenomena to explore. And yeah, yes. So Matt wanted to talk about a book that he's been reading, a quantum information scientist. I won't give him a cold open, of course, but I don't know too much about the book, but he found it really interesting. So warm welcome.
Everyone. My name is actually Michael, just for its information. This is a book, Programming the Universe. It's written by Seth Lloyd. A little bit of information about him. He was a famous quantum computer scientist. He made like one of the first like realized versions of a quantum computer. Worked at MIT. And then, interestingly, he actually went to Jeffrey Epstein's island, and now he doesn't work at MIT anymore. So just a little tip for everyone in case someone approaches you for a private jet trip to an island, don't go. But this book is very interesting. It starts off by talking about like what computation is, what information itself is, everything around us, every table, every chair has coordinates to them. They have information that holds them. And so the book kind of really dissects what exactly information is. There's classical information, zeros and ones, and then there's quantum information, which is, everything we've learned about, but we don't really know about quantum information. But I wanted to talk about a couple different concepts that he talked about in here. He talked about the reversibility of quantum computers. All the gates, well, we don't learn about any gates, but all quantum gates are fundamentally reversible. Now, what does that mean? Reversible? It's like if you run a gate 2 times in a row, then it'll like revert back to the original state. Like if you had a gate, classically, that was addition, right? And you put in 2 numbers, 2 and 3, and you get out 5. If I were to only give you this 5 and ask you what were the 2 inputs, you would have no idea. You'd say, oh, is it 0 and 5, is it 2 and 3? It's almost like a superposition of all those states. But quantum computing, since it uses unitary matrices to transform the state, it actually, the addition matrix would actually have another output, and that would be A minus B. That would be 1. And so let's call this A, B, A plus B, A minus B. And so with this gate system and other gates like it, you could have a quantum system that can go in this direction or in this direction, because these numbers can be reconstructed from these numbers. And so it's sort of like the information itself in the quantum computer isn't lost like it is in a classical computer. In a classical computer, the plus operation loses information and you can't go backwards. So that's a little bit about, quantum gates and stuff. Oh yeah, I wanted to talk about Maxwell's demon. Has anyone ever heard of Maxwell's demon? Oh geez, of course you have. So basically what it says is, imagine you have 2 rooms and they're both about equal temperature. In thermodynamics, we understand temperature as a microscopic property of all the individual atoms going back and forth. Like in this room, there are gas molecules moving probably like hundreds of meters per second, but like they're so tiny that we just don't know like where they are. We don't feel them because the force they impact doesn't really make us feel it. And so imagine that you have 2 of these rooms next to each other with a wall in between them. They're both the same temperature. And now Maxwell's demon is a little devil that stands at the wall and is able to open or close a door depending on whether a fast molecule is going into the door or a slow molecule is going to the door. And so if you, let me draw this out. Yeah. If you imagine this process that doesn't use any energy, assume that opening and closing the door doesn't take much energy. But there are particles, each with different velocities in here. And the demon stands here and you can either open this door or close it. So if the demon sees a fast particle move towards the door, he opens it real quick and closes it before any other particles can get out. And if a cold one is going this way, then we'll open it, let the cold one go that way and close it again. And so after a long enough time, all of the hot particles will be on one side and all of the cold particles will be on the other side. And this violates the second law of thermodynamics, like if you have 2 rooms that are equal temperature, they don't spontaneously like become one hot, cold. And so there's actually a very nice metaphor for Maxwell's demon that was solved in the book by using a C-naught gate. The C-naught gate is, it's right there. So essentially, like if you have a hot molecule come in, then it'll like switch the door up, like the 2 eyes, like 1, 1, 1, 0. This is for like if the door is being closed, like a hot molecule going to the left or a cold molecule going to the right, just leave it closed. But then here, if there's a hot molecule going in from the left, it'll open the door, and a cold molecule from the right, it'll close the door. And so essentially what that teaches us is that even though like a hot molecule may be going in from the right, the C-naught gate still conserves the total information, because the information of the door being opened or closed is not lost to the C-naught gate. it's preserved. And thus the second law of thermodynamics is, saved from Maxwell's demon. There's a long history of Maxwell's demon throughout, like Maxwell was from the 1860s until I think the 90s. And yeah, there's Maxwell's demons, Laplace's demon, various other demons and creatures. But that's Maxwell's demon. Very interesting synopsis of it in here. And then finally, I wanted to talk about simulation theory. Has anyone ever heard of that? Simulation theory? No? Well, before we were talking about how if you had two quantum states that were, both linearly independent, and it'll take four classical variables to describe them. And if you had three independent vectors, it would take 8 variables. And so it's an exponential relationship, 2 to the power of n. So if say you had, say you're a solid state physicist who's studying a crystal and you want to simulate what all the atoms in that crystal are doing, it would take a huge amount of computation in order to actually represent that system itself. But then if you had a quantum computer and you can actually match the rate at which the information in the solid state expands with your quantum computer, and it's a one-to-one transformation of completely describing this crystal, this state, or whatever the thing you want to describe is, you can do it perfectly with a quantum computer. And so that begs the question, like, what if this whole reality, the whole universe is built on a quantum computer? Well, there are 10 to the 82 atoms in the universe, and a quantum computer scales at like 2 to the n. And so that comes out to, I think, like if you had a 300 qubit quantum computer, you could simulate every atom in the universe. Now, it might not be perfect, but like that just gives you an idea for what the meaning of this all is. Because we run into quantum mechanics and we think it's so strange, these strange behaviors, but like what if those strange behaviors are just like the same strange behaviors that are up there in the sky? We don't know. I wanted to also read an excerpt from here that probably better summarize what he was talking about. So, a quantum computer that simulated the universe would have exactly as many qubits as there are in the universe, and the logic operations on those qubits would exactly simulate the dynamics of the universe. Such a quantum computer would be a physical embodiment of the Marquis Pierre Simon de Laplace's demon. It would simulate the behavior of the universe as a whole. Such a quantum computation would constitute a complete description of nature, and so would be indistinguishable from nature. Thus, at bottom, the universe can be thought of as performing at a quantum computation. Likewise, because the behavior of elementary particles can be mapped directly onto the behavior of qubits, interacting via logic operation, a simulation of the universe on a quantum computer is indistinguishable from the universe itself. Which is like, that's it. Like, there's no way for us to really distinguish whether or not we're living in a simulation. And so it's just something interesting to talk about and think about, because we'll never actually know the answer. But this book had a wonderful overview of the whole topic. This one professor, Daniel Yang, he says that learning physics and engineering and that stuff, like hard, like vectors and stuff, that's like drinking hard alcohol, like distilled, ever clear, just straight down. But a book like this is like a sweet wine that you drink to enjoy. And so that being said, I highly recommend this book, Programming the Universe, by Seth Lloyd.
Thank you, Michael.
I guess that's it, guys. Do you